The belief that anything more advanced than algebra is irrelevant has become ubiquitous, and it's easy to deduce why. Not only is advanced math confusing and tedious for the majority of people, but it also has little practical application outside of engineering and mathematics itself. So, people become disillusioned with the subject. However, this presumption relies on a fundamental misconstruction. Math is not made, it's discovered, and exploring the origins of math in the physical world may be enough to interest most people, even when ignoring the intellectual benefits that come from studying and understanding math. Let's go back to Archimedes, who made the greatest Greek contribution to the precursors of integration when he worked to find the approximate area of a circle. He performed the method of exhaustion by inscribing and circumscribing regular polygons and increasing the amount of sides they had infinitely. His proof proposed that the limit of the area of the polygons as their number of sides increased to infinity was equivalent to the area of the circle, though this was before limits had even been created. The sum of the triangles made from the polygons had a height equal to the radius and a base equal to the circumference. As the number of triangles approached infinity, the rectangle they made would present the area function of a circle. Ergo, foundational integral calculus. This use of infinity was disputed then, and its use continues to be controversial now, but this principle of approaching infinity is what calculus is built upon. This concept of infinity drove later major contributions to the field, from two mathematicians, Bonaventura Cavalieri and Pierre Fermat. Cavalieri created the method of indivisibles, which purported that a line was made up of an innumerable number of indivisible points, a plane made up of innumerable indivisible lines, and a geometric figure made up of innumerable indivisible planes. An area was the sum of these infinitesimal lines, and a volume was the sum of these infinitesimal planes. Fermat worked with the same ideas more rigorously, and his work with curves resulted in an equation for the tangent slope of a line that was very similar to our current limit definition for differentiation, and an equation for the area under a curve that telegraphed our own general integration power rule processes. Fermat also proposed a method of using the tangent to the curve when parallel to the x-axis to find maxima and minima. Now we reach Isaac Newton, who synthesized the foundations of calculus and gave us his gravitational epiphanies because of a falling apple. He would begin working with curves to solve problems that established calculus, one being the instantaneous rate of change at a point on a curve, or what you may know as the derivative. Newton established a fundamental theorem of calculus by determining that the area of a curve was the integrated equation of the first bound minus the integrated equation of the second. However, he hid these findings, and another mathematician, Gottfried Leibniz, independently discovered the same things and popularized them. In fact, the familiar notation we use originates from him. Also, Newton used fluxions and fluents in his explanations of differential calculus, which related position and time, while Leibniz performed differentiation with his dy over dx notation, which represented a ratio of infinitesimal movements towards the changing variable. Even with all of these discoveries, calculus was still trivialized as infinitesimals were still seen as mathematical fiction, and calculus was very reliant on infinity. The ostensible mathematical validity held by calculus would only become real later on, with the introduction of series and limits. Interestingly, limits tie back to Archimedes' exhaustion from the beginning of this video. Overall, math is as scientific and historical as any other subject, and learning the proofs and origins behind each formula could revolutionize curriculums and lift mathematics out of public disgrace.